In this lecture, we will discuss section 3.10, partial sums of partial sums of divisible product. Divisible product. First, we have a theorem 3.10. Theorem. It states that if H is equal to F star G, the divisible product. Let capital H of X is the partial sum of F star G, sigma n less than or equal to X, H of n, comma, capital F of X denotes the partial sum of F n less than or equal to X, F of n, and capital G. Capital G is the partial sum of G. This is G of n. Then we have H of X equal to sigma n less than or equal to X, F of n, G of X by n. In fact, this is the convolution of F and G. And this is also equal to sigma n less than or equal to X, G of n, capital F of X by n. The convolution of G and capital F. So this is the left side is the partial sum of divisible product of two arithmetical functions. Then you get that as the convolution of F and the partial sum of the other. We will prove this theorem using the associative property of convolution and star. Before that, we will define a new function u that is equal to 0 when 0 less than x less than 1, and the value is 1 for all other x. So if you define u like this, you can get capital F is equal to sigma n less than or equal to x, f of n into 1, that is equal to sigma n less than or equal to x, f of n u of x by n. Since this n is always less than or equal to x, this quantity is always greater than or equal to 1. So u of x by n is always 1. Okay? So this can be translated as f equal to small f convolution u. Similarly, if we start with g, you have the same result, n less than or equal to x, g of n into 1, that is equal to sigma n less than or equal to x, g of n times u of x by n, that gives capital G as small g convolution u. Okay, when you operate this with g, okay, or we can first f convolution g. Okay, what is this f convolution g? F convolution g gives f convolution g g convolution u. This is equal to f star g convolution u, that gives h convolution u. Okay, so you need to translate this. So this implies what is f convolution capital G? That's defined as first we can write this h convolution u. H convolution u is sigma n less than or equal to x, h of n u of x by n, that is always 1. So the right side will be this one, that is equal to what is left side, f convolution g. F convolution g is sigma n less than or equal to x. This f convolution g, we have f of n g of x by n. Okay. So we have this n less than or equal to x, sigma n less than or equal to x, h of n is nothing but capital H of x, that is equal to sigma n less than or equal to x, f of n g of x by n. This is what we have to prove. This is the first equality. Uh, if we start with that comes from this result. Now you take g convolution f. Then we have g convolution. F is obtained as f convolution u. So this is f convolution u. That is equal to, by associativity, g star f. We know that g star f and f star g are same. Convolution u, that is equal to h convolution u, that implies the same result, sigma n less than or equal to x, h of n equal to sigma n less than or equal to sigma n less than or equal to x, g of n, f of x by n. Okay. By translating that, you can get h of x again, that is equal to sigma n less than or equal to x, g of n, f of x by n. This is our result. So these are the two statements what you have to prove. That means we have h of x as sigma n less than or equal to x, f of n, g of x by n, that is equal to sigma n less than or equal to x, g of n, h of x by n. Here we know this h is the partial sum of divisional product of f and g, and capital G is the partial sum of g, and capital F is the partial sum of, here we have f, right? Here we have capital F is the partial sum of small f. Now if we define g of n is equal to 1 for all n, what is the partial sum of this arithmetical function n less than or equal to x, g of n? So that will be sigma n less than or equal to x 1, that will give integral part of x 1 plus 1 plus up to the integer which is just less than x. Okay, so that is equal to integral part of x. Okay, when you replace this in this equation, you can get an identity like this. If you define uh, small h as f star g, you can, what is the small h here? Small h is f star g. What is f star g? Small h of n is nothing but sigma d divides n f of n g of, so f of d, g of n by d, that is equal to sigma d divides n f of d, g of n by d is always 1. Okay. Now you can get this h of n is equal to sigma d divides n f of d, or you can consider this h as the device or some formula for f if we set g is equal to 1. Then we can verify this equation, h of x. First we have to find h of x. What is h of x? H of x is sigma n less than or equal to x h of n. That's the partial sum of h of n. That is equal to sigma n less than or equal to x. This h of n can be written as sigma d divides n f of t. Okay, this is the uh, h of x here, and now we have to evaluate sigma n less than or equal to x f of n g of x by n. That's equal to sigma n less than or equal to x. Here we have f of n g of x by n. We have g is this capital G is the partial sum of small g. Partial sum of small g is nothing but integral part of x. Okay, so this will be g of x by n will be integral part of x by n. Okay, now evaluate the last term sigma n less than or equal to x g of n of x by n. Okay, that is equal to sigma n less than or equal to x. G of n is 1 always, and this f is the partial sum of small f, then that will be equal to f of x by n. So since these three quantities are equal, we can get these three quantities are equal. Okay? So that is sigma n less than or equal to x, sigma d divides n, f of d equal to sigma n less than or equal to x, f of n integral part of x by n, that is equal to sigma n less than or equal to x, f of x. Okay, so these are the special case of the previous theorem when we replace that g by this function g of n is equal to 1 for all n. This is the section 3.10. Now we can move on to section 3.11. In this section, we can see an application of the previous result when we replace that f by mu of n and lambda of n. So first we write the result again. H of x can be written as sigma n less than or equal to x, f of n. Here we have g of x by n, that is equal to sigma n less than or equal to x, g of n f of x by n. Okay, first we will replace this f as mu and g as the same function what we have defined in the previous theorem, g of n is equal to 1 for all. Then what is sigma n less than or equal to x f of n? That is sigma n less than or equal to x mu of n. And we have sigma n less than or equal to x g of n. That is capital G of x, that is equal to integral part of x. Now we have h is equal to mu star g. Okay, what is mu star g? H of n will give sigma d divides n mu of t, g of n by this one. Okay? And this is equal to integral part of 1 by n, because this is the divisor sum formula for mu. Okay, so sigma d divides n mu of d is equal to integral part of 1 by n. Okay, these are the uh, changes in that theorem. Then we have just proved that using this idea we just proved that sigma n less than or equal to x, sigma d divides n f of d equal to sigma n less than or equal to x, f of n into integral part of x by n. that is equal to, obviously that is equal to sigma n less than or equal to x f of x by n. There, so we use this equality. Okay, from this equality we can write sigma n less than or equal to x. Sigma d divides n f of t, we replace this f by mu, then we can get sigma d divides n f of d as sigma d divides n mu of d, that is same as integral part of 1 by n. So we can write it as integral part of 1 by n, and this will be sigma n less than or equal to x. This is f of n. F of n is nothing but mu of n, and this is x by n. That implies sigma n less than or equal to x mu of n into integral part of x by n equal to, when you expand this sum, for n equal to 1 we can get this term is 1, and for all other values we have 0, so this is equal to 1. Okay, now if you replace this f by lambda and g by the same function, you can get sigma d divides n f of d is equal to sigma d divides n lambda of d, and this is proved as log n. Okay, so if you consider this equation again, you can write it as sigma n less than or equal to x log n, because sigma d divides n f of d is same as sigma d divides n lambda of d, that is log n, that is equal to sigma n less than or equal to x lambda of n x by n. Okay. This implies sigma n less than or equal to x lambda of n integral part of x by n equal to, when you sum up all this, you will get log 1 plus log 2 plus etc log of integral part of x. Okay, so that can be written as log of 1 into 2 into 3 into etc integral part of x, that is nothing but log of integral part of x factorial. These two formulas are called weighted sum, weighted sum of mu and lambda. Okay, these are two important sums, so these are called weighted sums. It says that for all x greater than or equal to 1, we have sigma n less than or equal to x mu of n by n, absolute value of this, which is less than or equal to 1. Okay, here equality holds only if x is less than 2. If n is if x is less than 2, the only possible value of the sum sigma n less than or equal to x mu of n equal to sigma n less than or equal to 2. So we have n less than 2 mu of n by n that contains only one tail. Okay, so that is the only possible value of this n is 1. So we have mu of 1 by 1, so that is 1. So we have equality here. In other cases, if x is greater than 2, greater than or equal to 2, we need to prove this inequality. For each y belongs to R, this y can be written as integral part of y plus fractional part of y. Clear? So we start with the result we have proved in the previous theorem. 1 is equal to sigma n less than or equal to x mu of n integral part of x by n. And this integral part of x by n can be written as x by n minus fractional part of x by n. And we distribute this mu of n sigma n less than or equal to x mu of n into x by n minus summation n less than or equal to x mu of n into fractional part of x by n. Right? So from this you can write, actually we need to collect this term. So sigma n less than or equal to x mu of n by n. Since this sum depends only on n, we can take this x out. So that will be x times this sum equal to 1 plus summation n less than or equal to x mu of n times fractional part of x by n. Okay, so when we take the modulus of this, since this x is positive, you can take modulus here. That is equal to modulus of this one, that is less than or equal to 1 plus sigma n less than or equal to x modulus of this quantity. Modulus of mu of n is 1 and modulus of x by n, fractional part of x by n. Fractional part of x by n is always positive, so you need not worry about the absolute value. So that is always same as fractional part of x by n. So this can be written as 1 plus, we extract the first term, so that will give the fractional part of x. If you put n is equal to 1 here, you will get the fractional part of x. Then we have some 2 less than or equal to n less than or equal to x fractional part of x by n, that is equal to 1 plus fractional part of x plus, since this fractional part of x by n is always less than 1, so this is always this quantity is always less than 1 plus integral part of x plus integral part of x minus 1. Because when we sum up all this, 1 plus 1 plus 1 plus up to integral part of x, here the variation of n starts from 2, so that's why this is integral part of x minus 1. So this will give, now you cancel this x with this one, you can get modulus sigma n less than or equal to x mu of n divided by n is always less than or equal to 1. Here if x is greater than or equal to 2, we can get strict inequality here, and for any x less than 2 we have equality. So in general you can conclude this summation n less than or equal to x, absolute value of summation n less than or equal to x mu of n by n is always less than or equal to 1.